Okay, I think we can start. Yeah, it's the time. So thanks everyone for coming to this to the talk of Laura Nenzi. We're very happy to welcome Laura from the University of Trieste. Laura is an expert in formal verification and statistical model checking for stochastic systems. And so since 21, she has been a tenure-track system professor at the University of Trieste. And she has a double degree in biotechnology and mathematics. And she did her PhD at the IMT Lucca in Italy. And then Laura was a fellow at the Technical University of Vienna in Austria, fellow of the Austrian Science Funds for Young Independent Research Groups. And she also received the Hedy Lamarr Award 2020 by the city of Vienna. That is a recognition for women in Austria for their exceptional achievements in the field of information technology. And the talk will be titled A Logic-Based Approach to Specify, Monitor, and Learn Spatio-Temporal Behaviours. And just before I let Laura speak, I would like to tell to everyone that Laura will be here until Thursday. And we have another visitor, postdoc Francesca Cairoli, also from University of Trieste, also an expert for formal verification and especially machine learning. And if you want to meet individually Laura and Francesca, we will go today for lunch here after the talk here at the university, and until Thursday we could make slots for individual sessions, and on Wednesday afternoon we will make a joint workshop for everyone from the cluster who is interested to discuss together. So now the floor is yours.
Thank you.
Thanks for coming.
So, good morning to everybody. So, Tatiana told me that the cluster has people from very different backgrounds, so from mathematics, but also psychology and biology. So, in this talk, I'm trying to be like very general and give idea of what I'm doing. But please, so if at the end you are interested in some topics, tell me. And also, I mean, I worked for a while in biology, but in the last year I worked more with the cyber-physical system. So my example that you will see in biology are a bit old, but I'm still interested in biology, and it's part of my first 5 years. So yeah, that's the beginning. So as I said, this is a talk about a logic-based approach to specify and monitor and learn spatio-temporal behaviors. So here I give you some example of a system. We can see here a wireless sensor network. This is an example of formation of pattern. It's a reaction diffusion system. Here we have mobile phone traffic data in Milan. And here we have a bike sharing system. So what they have in common is that they are all systems that are spatially distributed. And actually, the spatial configuration is one element that is often not taken into account when you model or study the system, because it makes the model much, much more difficult. So what I will try to show you now is how we can specify behavior as the formation of pattern or for example, the reliability. But let's see some couple of behaviors in words, and then we will see later how we can specify such behavior. So to give two more specific example, for example, in a bike sharing system, so you have a number of bike stations in a city where you can pick up or bring back a bike. And one behavior that you would like to have is that I can eventually, in the next 5 minutes, find a station with at least one bike in a radius of 500 meters. Another example is I have a wireless sensor networks. It means that I have a number of sensors distributed in space that can check some, for example, the temperature or the humidity in that region. And one behavior that I would like to specify and monitor could be, we can always find a path of sensors such that all sensors have a battery level greater than 0.5. Okay, so this is our behavior that I describe in words. And we will see how we can use a logic to describe that behavior. Before that, I want just to say something more about the type of system that I study. So they are in general called complex systems, but collective adaptive systems are an example of complex systems. And usually are systems with different entities that should interact in a nonlinear way. And usually this nonlinearity brings to an emergent behavior that cannot be derived from the single entity. Plus, they have often an inhomogeneous spatial distribution. And last, I usually study large-scale systems. So systems for which there is a large area of formal methods where you have exact verification techniques. So that techniques for very large-scale systems are not possible. It's not possible to use that techniques. Okay, so in this talk we will try to see how we can specify such spatio-temporal behavior in a formal and human understandable language. So what does it mean to have a specification-based monitoring? So what does it mean to have a formal specification? Here we can see a very simple example. So first, we need to describe our system. As I say, we are working with a large-scale system, and so mainly we will work with the simulation of this system, or even directly with the real data. So you have your model that you specify as a differential equation or continuous time Markov chain or hybrid system. You simulate your model, and then you have a trajectory. Similar, you can directly have data from some real sensor, and from the real sensor you have a trajectory. So these are the type of evolution that we will able to specify and monitor. Okay, so we have some trajectory, so evolution in time of some variable, and we want to specify something like between 2 seconds and 4.5 seconds, the output signal is between -2 and 2. So what I say here in word can be described with a logic formula. So here there are some specific symbols that are used to describe, for example, the evolution in time. So here the fact that it's always true between 2 seconds and 4.5 seconds that the signal is between -2 and 2 is described by this symbol, G, that means always. Okay, so you have some specific symbols that are used to describe the dynamic evolution of your system. Okay, and then, so given your simulation or real data of your system, and given the specification that you specify with the logic formula, then the logic has specific called monitoring algorithm that can be used to check in an automatic way if your trajectory satisfies or not the property. Plus the type of logic that I use has also 2 different possible verdicts. So you can have a qualitative verdict that tells you just if the trajectory satisfies or not the property. So you have a 0-1 answer. Or you can have also a quantitative verdict. So a real value that can give you like a an evaluation of how well your property is satisfied. So how well your trajectory satisfies the specific property. And we will see later better what's the meaning of this quantitative verdict. So this is the general idea. You have a certain trajectory that specifies the evolution in time of your system. You specify your property with a formula, and then you can check in an automatic way such specification. Why it can be useful to have a logic language? It can be useful because a logic language is formal, is a not ambiguous language, and is a pretty human and understandable language. Pretty because, of course, you have to learn the meaning of the symbol that we are using. Okay. So, but I give you just a trajectory there, and what we will see is a spatio-temporal system. So just to give you an idea of a spatio-temporal property, here is again the formation of pattern. So this is the evolution in time. You start with a very random concentration of a certain protein, and at the end you arrive with a stable formation of, let's say, spot. So a possible behavior that you would like to check is that within 20 time units, the expression of the protein stabilizes low in the blue region and high outside. So what I've said in this in words can be described with this logics formula, and we will see this later. Okay, so I cheated a bit because I say, okay, we have a trajectory and a specification, and we can check if the trajectory satisfies or not the specification. But actually we have a spatio-temporal system, so we don't need just to know what is the evolution in time of our system, but we need also to define what is the spatial configuration of our system. So what we will see now is first how we describe our system. So how we describe the spatial configuration of our system, and how we describe the evolution in time of a spatio-temporal system. Oops, sorry. Then we will see how we can specify the properties. So we will see a bit more in detail the logic. And finally, we will see several examples of case study. Okay, so how do we describe our system? So as spatial configuration, we consider a discrete space described as a weighted direct graph. So our system we will always describe just as a graph. So where you have a number of nodes that can be connected in some way. Why do we decide to use this kind of spatial configuration? Well, there are two reasons. First, there are many applications like the bike sharing system, the smart grid, the sensor network that are naturally framed in a discrete spatial structure. And second, in many circumstances, even if you have a continuous space, this can be abstracted as a grid or as a mesh. As the example that we have just seen, if you have the diffusion in the space of a protein, you can describe this as a grid with a number of cells. Okay. So our spatial configuration is described as a space model where we have a set of locations and we have a proximity relation between locations. This proximity relation has also a certain label with a center weight. So that means that we have a number of locations that are our nodes and a number of edges, and each edges can be a different value. Okay. So let's use an example from now on to understand a bit better what I'm meaning. So as an example, we are using just a sensor network. So you have a number of sensors that are distributed in a space. And from that, you can define different types of graphs. Let's see just one graph. The simple graph that you can describe is the connectivity graph. So it means that two different sensors are connected just if their radius, the difference, so from a radius from one, so let's say the distance between the two different nodes is less than a certain threshold. So if each sensor has a certain radius, if the two radius interconnect, let's say, then we say that there is an edge between these two sensors. So given this relation, we can build the connectivity graph of a number of sensors. Okay. Just to give you another example, the simplest but with many edges that you can build as graph is just to connect all nodes with all the other nodes. Is a fully connected graph, is a very complex graph, and you can consider just the Euclidean distance. Okay, this is another possibility of graph. Okay, so we have a number of locations that are connected in some way, and then what we need now is to describe the evolution in time. So if you think again to the sensor, you can think that these sensors have a certain level of battery, or for example, they are recording the humidity or the temperature in the position where they are. So a spatio-temporal trace means to describe the evolution in time of these different signals in each location. So each sensor, it has its own evolution in time of the level of humidity or evolution in time of the level of battery. So we have a number of locations, in this case sensor, and each sensor has a number of signals, one for each different variable that you are considering. Okay, I just make a bit more complex our simple sensor network, because now we are considering different possible type of nodes. So these are all sensors, but we have a coordinator. The coordinator in a sensor network is the ones that start, let's say, all the wireless or start like activate all the other sensors. Okay, so in a mobile ad hoc sensor network, you have the coordinator that activate all the other sensors, and then you have the router that are the ones that can, let's say, communicate directly within each other, and instead the end device can communicate just with the router. So let's say you can have different type of sensor. And here, so we describe a bit more complex spatio-temporal model. So we have a number of locations that are our sensor, our devices. We have an edges just if they are within their communication radius. And then we have the spatial temporal trajectory is composed of 3 different signals. So each sensor will have the type of node, if it's a coordinator, a router, or an end device, and then the level of the battery and the temperature that change in time. Okay, so now we have a way to describe the space, so as a graph with edges. We have a way to describe the evolution in time, so we have a spatio-temporal trajectory. And now we are going to describe, to specify the property. So here is the syntax of the spatio-temporal reach and escape logic. You don't have to understand all these symbols, but I wanted just to show you the syntax. And now we will see the different symbol in each slide. So actually this is, as I say, is a spatio-temporal logic, and is an extension of a temporal logic that is called the signal temporal logic. Okay. So the first type of symbol that we see here is the atomic proposition, here. And atomic proposition are just inequality over the signal. An example is just to say the battery is greater than 0.5. Okay, so the atomic proposition are the, let's say, smallest element of the logic and are used to describe the single behavior of the variable, as for example, say that the battery should be greater than 0.5. Then you have the Boolean operators that are just and, or negation. So for example, you can say that the battery should be greater than 0.5 and the temperature should be less than 30 degrees. Okay. And then you have the temporal operator. We have already seen the always operator at the beginning. So these are used to describe the dynamical evolution of the system. So the eventual operator is used to describe something that should happen in the future in a certain time interval. So here, for example, you have eventually in the next 3 hours, the signal x is greater than 5. So here we have an example of a signal, and this means that this is the symbol for the eventually. In the next 3 hours, so from 0 to 3, the value of the signal x should be greater or equal to 5. Okay. The always operator instead is used to describe that something that should be always true in a certain interval. So here, for example, we say that the signal S is always between 1 and is always true between 1 and 3 in the time interval 0, 24. Okay. Then you have also the until operator, which is a bit more complex, and we will skip it. Okay, so we have some operator to describe the dynamic evolution of our system, and then now we will see some spatial operators. So the spatial operators are used to describe some spatial behavior of our system. The simplest one is the somewhere operator. The somewhere operator, this is the symbol for the somewhere operator. This means somewhere at the distance between W1 and W2 phi, requires phi to hold in at least one location at the distance between W1 and W2 from the current location. Let's see a simple example. Here we have the property somewhere between 2 and 3 purple. Here we can see that, for example, the location L1 satisfies this property because there is at least one location at the distance between 2 and 3 where the purple property is satisfied. Okay. Then we have the everywhere operator, where the difference between the previous one and this one is similar as the eventually and the globally. Here we want that all the location at the distance between W1 and W2 satisfy a certain requirement. So let's see directly the example. Here we have everywhere between 2 and 3, yellow. So here, for example, L1 satisfies this property because all the locations that are at the distance between 2 and 3 from that location are yellow. Instead, for example, L2 does not satisfy this property because there is at least one location here that is at the distance 3 but does not satisfy that property. Okay. Then we have the reach operator. The reach operator, I'll give you just directly the example. The idea is that you can reach a certain location that satisfies a property through a path that satisfies another property. So, for example, yellow reach between 1 and 4 green. It means that a location satisfies this property is from that location I have a path of a yellow location that can reach a green location at the distance between 1 and 4. Okay, so this is used to have a path that satisfies a certain property, phi1, and that reach another path that satisfies another property, phi2. Okay, just last one, and this I give you just an idea because it's a bit more complex. We have also a surround operator. The surround operator is used to describe when you have a certain region that satisfies a property that is surrounded by a region where all the nodes should be connected, all the nodes that are connected of this region they should satisfy another property. So let's see an example. Here, for example, green surround blue. It means that I have a region where all the locations satisfy the green property, and all the connected region on this location should satisfy the blue property. And then we can, like say, play with the distance constraint to change the location that satisfy the property. But I will skip this. Just give you the idea that you have a certain region that satisfy, for example, green property, surrounded by nodes that satisfy the blue property. Okay. Okay. So this was just an overview of how we can describe the model, let's say the system, and the operator, and let's see now some examples that maybe can help you to understand better what does it mean. So here we have in words this behavior. An end device is either connected to the coordinator or can reach it via a chain of at most 5 routers. What does it mean? It means that, as I say, the coordinator is the sensor that activates all the network, and the end device should be connected directly to a router to work. So here it means that the end device reaches directly some location that satisfies this property. So a location that either is a coordinator or is a route that can reach in few steps, in few locations, a coordinator. But we can even have a more complex property from this. Let's say that, well, okay, this is good, but we would like that a broken connection is restored within H time unit. So we don't need that is sensor is always connected, but what we want is that if the sensor is not connected anymore, this is the negation of the connection, then eventually in H time units it will be reconnected. Okay. And this was one of the properties that we have seen at the beginning. That was the reliability in terms of battery level. And here, so we are asking again that the router reach the coordinator, but here we are also saying yes, but the router should have also the battery with the level more than 0.5. Okay. Okay, so this was to give you an idea of the type of property that you can describe with the logic. And now I wanted just a bit to discuss about what you can do with this. No? So you have your spatial configuration, you have your spatio-temporal trajectory, and you have your specification. So these logics come with some monitoring algorithm that can check in an automatic way if your system, if your trajectory satisfy or not the property. So the result after the monitoring, it will be something like this. So where for each location, you will know if that location satisfy or not the property. Okay. But what I say before is that we have two possibilities, or just 1, 0, 1 verdict. so just to say if the location satisfies or not the property, or you can have also a quantitative evaluation. So what's the idea of the quantitative evaluation? As I say, the idea of the quantitative evaluation is that instead to say just this is true or false, you give a real value that gives you the quantification of how well the property satisfies. So if this value is greater than 0, it means that the property is satisfied. If it's less than 0, it means that it's not satisfied. Or just to give you a more like flavor of what it means, here we have a very simple signal, no? And we are just asking that it's always true between 50 and 100, that the signal is less than 3, okay? Here we see that this is more than 3, so this is bad. This is not a signal that satisfies this property. Well, this distance, it will correspond in the quantitative semantics how bad is the violation. Here instead we have an example of a signal that satisfies the property, because here the signal is always less than 3, and here the distance that we have between the signal and the threshold, 3, it gives us an idea of how far is from becoming a bad trajectory. Okay, so coming back to the sensor network, so here we have we have just few nodes, but actually we can work with many more nodes. But was too crowdedness was not good to show you the behavior. So here we have the nodes that are moving in the space, and here we are checking these properties. So the fact that the device reach the coordinator or the router in a number of steps. Okay. Should I want to show you, okay. So the meaning, the fact, the meaning of the fact that a specific node satisfies or not the property. No, it doesn't want to go to the end. Okay. So here you can see that the only location that does not satisfy the property is this one, the red one. So the blue nodes satisfy the property, and the red one does not satisfy the property. So if you can see here, these are the end devices, the yellow nodes. If you can see here, the 14 is the only end device that is not directly connected to a router. Okay. Okay, it doesn't want to stop. Okay, so how does it work actually, the monitoring technique? Actually, you have a specific monitoring algorithm for each operator. So you have a monitoring algorithm for the temporal operator, for the Boolean operator, for the spatial operator. Each different operators has a different monitoring algorithm. I wanted just to give you some consideration about some computational consideration about the monitoring techniques. So actually the temporal operators are pretty fast, and they were already fast in the signal temporal logic, and the monitoring is linear in the length of the signal and the number of the location in the spatial model. The spatial properties instead are more expensive, and the number of operations to perform can be, in the worst case, cubic. But we have to say that most of the computational time is given to compute the distant matrix. So if instead to have a dynamic model, you are working just with a static model, the computational time is much slower. Okay, so this was really just an overview of how you can specify with spatio-temporal logic, spatio-temporal behavior. These kind of techniques can be applied in different type of scenario. It means both different type of modeling, but also different applicability, as for example, parameter synthesis, monitoring, and learning. I didn't write. So here is just an overview of things that I thought could be interesting for you, and if you are interested, we can discuss later. So what I've seen before is just a sensor that is described as a number of nodes, but as I say, you can also describe a grid as a graph. So here is an example of studying the formation of patterns, where we have, for example, here is the evolution of time of two proteins. It's a reaction diffusion system. So there are two proteins that diffuse in the space and interact in some way. And at the end, what you have is here you have just evolution of one property, is the formation of this spot. So area where there is a very low level of concentration of a certain property surrounded by area where the concentration is very high. And here, so the spatial model is described, as I say, is a grid. Each cell is a single location, and the edges are just the connection between the neighbor. So neighbor cell have an edges that goes from the single cell to the neighbor. Okay. And here the spatial temporal trajectory is just that in each location we are considering the concentration of these two proteins, A and B. And here we see just the protein A. Okay, so for example, we can describe the formation of a spot with this property. This means that eventually in the future, from a certain point on, it's always true that the concentration of protein A is very low, and this region where the concentration is very low is surrounded by the region where the concentration is very high. So here there is opposite colors. So actually the red point are the points that satisfy the property, and the blue one are the ones that does not satisfy the property. And here we have the quantitative semantics, where here we have the legends of the value of the satisfaction. Okay, but with this we are describing just the single spot, no? We were just describing local property. So actually there is a way to describe even the whole pattern using the other spatial operator. This means that is always true, and if you take like a distance, something that takes all the graph, it means that if you just take one single location, you can consider all the possible location of your graph. And here you say, okay, from all the location is always is true that somewhere I have a spot at the distance between 0 and 50 units. So this means that this is able to describe the fact that from a certain location you will always find between 0 and 15 units a spot. And actually this way to describe the pattern is a property that is satisfied by this evolution, but is not satisfied by this evolution. These are so we were able to simulate also this pattern, just changing the diffusion rate in the reaction diffusion system that we simulated. Okay, So what we have seen until now is just using the logic to monitor a single trajectory. So actually this can be used also if you have a stochastic system. So what's the idea? A stochastic system can be described as a set of trajectory, no? So the idea is that you can monitor the satisfaction on each single trajectory, and then let's say you can make a mean of this satisfaction. This is the main idea of the statistical model checking, and something similar for the quantitative semantic. So given a stochastic system, you simulate several times your system, you check the trajectory for each you check each single trajectory, and then you make a mean, let's say, of the result. So this is the idea. So you simulate your system several times, and then what you have at the end is, if you are considering the Boolean verdict, you have a probability satisfaction, and if you're considering instead the quantitative verdict, you have an average robustness, so a mean of the quantitative satisfaction. So here is an example where we use when we monitor some spatial temporal property on a stochastic system. This is a bike sharing system, and these are the maps of the bike station in London. And we consider a very large system with around 800 bike stations, and we model this system as a stochastic system, in particular a population continuous time Markov chain, and we were able to predict the next 40 minutes. So in this case, the spatial temporal trajectory corresponds to the number of bike and free slot in each bike station. And the spatial model the location are the bike station, and then we're considering to have an edges between two different stations, just if the two different stations are at a distance less than 1 kilometer. And this is the property that kind of property that we considered at the beginning. So we want that from a specific location, we can always find a station at the distance t where there is at least one bike. So the number of bike is greater than 0, and there is at least one free slot. So the number of free slot is more than 0. And here we can see some result changing the distance. So what does it mean here? Here we have these are each node is a different bike station, and here we have the probability satisfaction of this property. Here at distance 0, it means that a certain location here satisfies this property only if in that location there is at least one bike and one free slot. Here we are increasing the distance. It means that here, even if I have a location that is at the distance of 200 meters from my location, it's okay if there is in that location at least one bike and one free slot. So, and you can see that when we are increasing the distance, so if for us it's enough that there is a station that is more far away from us where there is at least one bike and one free slot, the location that satisfies the bike station that satisfies the property increases. So at 600 meters, we can see that almost all bike stations has at least one bike station closer at 600 meters where this property is satisfied. Okay, I go directly on the last two things that I wanted to describe. So the fact that you describe a behavior with a logic can be used also to do parameter synthesis on your system. So you have a certain model for which you don't know some parameter of the model, and we want to find the parameter that maximizes the satisfaction on a certain logic formula. That means that maximizing the quantity that I have described as average robustness, so the mean of the quantitative satisfaction. So this, just to give you a biological example that I've done quite time ago, here was a model that described the diffusion in the space in a Drosophila of a morphogen. The morphogen is a kind of protein that can activate different kind of gene with when it has a different concentration. Okay, so here you have the diffusion in the space of this bicoid, and you can see that when the concentration has a certain threshold, there are 3 different thresholds here, it can activate different type of gene, and then this brings to different type of segmentation. This is also called French flag model because there are like 3 different thresholds, and it's like the French flag. So what's the idea here? We define a model distributed in the space where we model the diffusion in the space of this bicoid morphogen, considering a number of cells. And then we describe with the logic these properties. So we define 3 different regions where there were 3 different concentrations of the protein. We decided the regions considering real data, and what we have done then is to optimize the parameter of the model, in particular the rate of the production, the degradation rate, the diffusion rate, in a way that that model with that parameter satisfies as more as possible the property that we define. And here is the result. We can see the observation that we had at the beginning, and here is the simulation of the model with the best parameter. Just to let you know, what I said until now is that we have a single trajectory, and we can monitor such trajectory. We have done some work also considering the fact that we can miss some data in the spatio-temporal trajectory, or we can have noisy data. So we have also another more complex monitoring algorithm that are able to work with not like just a single trajectory, but like with the uncertainty trajectory, and even with missing data. And last thing we have a number of work now where we are trying to use the logic instead just to, okay, we write the formula and we monitor directly the formula. We are trying to learn the formula directly from the data. I will not go in detail this because it's too complex, but I will just to give you the idea of the type of problems that you can effort. So you can have 2 different types of data we're considering. Labeling data, so where you know, for example, already that you have a set of regular trajectory and anomalous trajectory, or you can have totally unlabeled data. And this brings 2 different possible solutions, let's say learning techniques. In the first one, when you have labeled data, the idea is that, okay, I want to find a formula that can be discriminate between the regular trajectory and the anomalous trajectory. So a formula that is satisfied by the all regular trajectory and is not satisfied by the anomalous trajectory. In the second case, instead, when you have unlabeled data, the idea is that, okay, I want to find different formula for each different cluster. So I want to try to clusterize my data, not considering just machine learning clustering algorithm, but using the logic. And at the end, I will have a different property for each cluster. And just to give you 2 examples on that. So here we study a disease that is called ineffective inspiratory effort, and it's a problem that have when you have the mechanical ventilation that are used to help the patient to breathe. It can happen that they are trying to breathe in the wrong moment, and so this causes the fact that you have a longer expiration phase. This brings 2 different types of trajectory of the flow of the airs in the axe. So here we have, we can see in the red the anomalous trajectory, and in green the regular trajectory. So what we have done here is to study such trajectory and try to find a formula that was satisfied by the green trajectory and not satisfied by the red trajectory. And here is an example of a formula that we found. This means that eventually between 31 and 130, the flow air in the axe is more than minus 67, which means, if you can see, the only, let's say, trajectory that goes in that area are the anomalous trajectory. Okay, and last thing, this is an example of instead cluster of data. Here we study a smallest bike sharing system, is the bike sharing system of Edinburgh. And the idea here is that instead you have a kind of template of the formula for which you don't know the parameter of the formula, but you know the shape of the formula. And we use that to, for example, if you remember, I use this one because it's the same that you have seen before. We have a formula that describes the fact that I can find a location at a certain distance, that is the phi walk, but I can also say, okay, I don't want to reach another station, but I want to wait a while and see if a bike will arrive in a certain time. Then we were studying all the data considering these 2 properties. So the fact that I can reach another station at a certain distance, or I can wait a while. And these are the result. So here is how the data are divided with respect to the parameters. Here is the minutes that I'm waiting, and here is the meters that I have to do to reach another station. And we found 3 different clusters. So most of the locations were like having the desirable behavior, so reasonable time to wait and reasonable time to reach reasonable distance to another location. But we found also few stations that had some problem. One in the city center where you should wait a lot, and 2 that are far away from the city center, where even both the time to wait and the distance was a lot with respect to property. Okay. Okay, I finish here. I hope that you have at least a bit an idea of what does it mean to describe a behavior with a logic formula. And we have a tool with most of the things that you have seen. I didn't put the references here, but I can give you, if you are interested in anything, I can give you later. And I think I'll finish there. Thank you.
So thank you, Laura, very much for this inspiring talk. Now we will have, I think we have some time for questions from the audience here and also from the online audience. I guess that is possible, right?
So thank you very much for the very interesting presentation. I think I have a couple of questions. The one is, the STL is mainly used for describing monitors, I understand, right? Is there also some work on doing reasoning about it? And can you say something about the, for instance, decidability properties, complexity of the logic?
Well,
Second
yes.
question, sorry, if I may just add that, can you tell us a little bit more about the different monitoring algorithm for the different spatial operators that you alluded to?
Yes.
Thanks.
So, here. Yes, so as you know better than me, model checking is not something that is possible with this kind of system that we are using. And monitor means that you are going to check the single trajectory. Maybe I have, okay, so the idea in monitoring is that you have a certain formula and you can derive the tree of this formula. It means that, for example, it's not written here. It means that, for example, eventually x greater than 5 means that you have the leaf, the atomic proposition, and then you go upper, where you have the sub-formula, and then you have the whole formula. So then, when you have this kind of tree, you start from the bottom in the monitoring algorithm, and you check first the atomic proposition, and from that you derive, let's call it the secondary signal. That means just the evaluation of x greater than 5 will become as secondary signal x minus 5. Okay. Then you have the secondary signal, and then when I was saying you have a specific monitoring algorithm for each operator, it means that when you reach the next sub-formula, you're considering the monitoring algorithm of the specific operator that there is in that formula. For the signal temporal logic, there is this Legmore algorithm that is linear in the time of the formula. It means that you need just to compute the next time step, and it's fine. Instead, for the spatio-temporal operator, it works with the so-called classic Floyd-Warshall algorithm. So the idea is that from my location, I'm going to check first just my neighbor and compute the evaluation for the neighbors, and then I'm going to compute the evaluation for the neighbors, and so on. For the reach operator, actually it's just quadratic. When I say cubic, is that we have also another operator that I didn't describe because it's too complex. It's the escape operator, where instead you need to describe, the shortest path. And when you have the shortest path, you need to know the matrix, the distance matrix, and this is it becomes qubit because you have to reach the whole graph. So you need to know. In the worst case, you need to reach the whole graph, and you can have an edge that goes from the first location to the last. And so it becomes cubic. And it's undecidable, absolutely undecidable. Yes. You're welcome.
We also had some questions in the chat.
Yeah, thank you very much for the talk. It's very interesting to me. I was wondering if you have multiple properties in your expression, and you want to do the quantitative evaluation. How do you get the metric space for that?
Well, usually we are checking just one property. If you have more property and you want that all the property are satisfied, it means to do like a conjunction of this property, and so you take the minimum value of the whole property. So usually what we are doing when we want to check more property is to take the conjunction and taking the minimum value. Instead, if you want to have consider at the same time more values, so more property, you have just more spatial satisfaction. So you have just more graph that describe each property. I don't know if I answer.
So maybe let's think of the example of the bike sharing in London, and imagine that we are interested in the expression that we want to have maybe 2 bikes nearby or within a range of 100 meters or so. And then imagine the case where there's only 1 bike, but maybe within 100 meters, but 2 bikes in 150 or so. How do you trade off these 2 properties if you want to assess how well is it satisfied or not satisfied?
Well, this is one of the, not problem, but one of the point in having just one single formula. It means that you have one single result. There are many works that are also like showing the satisfaction, for example, of the sub-formula, no? So as I say, you can think to the formula as a tree, no? So if in your example you have a conjunction, no? It means that you can, in the tree, you will have one sub-formula that is the part of the distance, one sub-formula that is the part of the weighting. So in that case, if you see if you check, if you monitor, if you take a look also to the signal of the sub-formula, you can see what is like the sub-formula that is more satisfied or the sub-formula that is more violated. I think that's something that is done when you want to, like, okay, this formula is not satisfied. Let's have a look what is the part of this formula that is violated. There are several works on that.
Thank you.
You're welcome.
Any more questions? Doesn't look like right now. So Laura, please let me thank you also on behalf of the cluster for being with us today. And as Tatjana already mentioned, if you would like to get more in exchange with Laura and also Francesca, it's best to approach Tatjana